Ett år har gått. Välkomna till den här presskonferensen där vi ska presentera årets Nobelpris i fysik.
Welcome to this press conference where we will present this year's Nobel Prize in Physics. As usual, we will start in Swedish and then continue in English. But when we have the question time, you are of course free to pose the questions in either language. Ja, jag heter Staffan Normark, jag är ständig sekreterare här vid Kungliga Vetenskapsakademin. Och med mig som sakkunniga bisittare har jag 3 fysiker. Till höger sitter professor Björn Jonsson, ordförande i Nobelkommittén för fysik, som kan svara på frågor kring kommitténs prisarbete. Och längst till vänster om mig har jag professor Per Delsing, ledamot i Nobelkommittén för fysik, och närmast professor Anne Lullier, även hon ledamot i Nobelkommittén för fysik, och dessa två ska snart förklara prisområdet mer ingående. Årets fysikpris handlar om växelverkan mellan ljus och materia. Kungliga Vetenskapsakademin har idag beslutat utdela 2012 års Nobelpris i fysik till professor Serge Haroche vid Collège de France och École Normale Supérieure, Paris, Frankrike, och professor David J. Wineland vid National Institute of Standards and Technology och University of Colorado, Boulder, USA. Akademins motivering lyder: för banbrytande experimentella metoder som möjliggör mätning och styrning av enstaka kvantsystem. This year's Nobel Prize in Physics is about interaction between light and matter. The Royal Swedish Academy of Sciences has decided to award the 2012 Nobel Prize in Physics to Serge Haroche at Collège de France and the École Normale Supérieure, Paris, France, and David J. Wineland at National Institute of Standards and Technology and University of Colorado, Boulder, USA. And the Academy citation runs for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. Professor Björn Jonsson will now give us a short summary in English, please.
Thank you very much. Yes, there was this year, Serge Haroche and David Wineland, they work in a field of physics called quantum optics. This is a very active research field, and it studied the fundamental interactions between photons, light particles, let's say, and matter. In fact, when we look at each other today here in the room, it's the interaction between light and matter that makes us see each other. The Nobel Committee has especially singled out the groundbreaking inventions made by the laureates that has led to the possibility to measure and control individual quantum systems. This is something physics has dreamt about since the dawn of quantum mechanics, and today it's a possibility. The method has, in fact, many things in common. There are 2 different methods. David Wineland, he traps charged atoms, we call them ions, controlling in an electric field. And then he controls them and measures them with photons, which are the particles of light. Serge Haroche, on the other hand, takes the optics approach. He controls and measures trapped photons. He traps them between 2 mirrors. And then he sends atoms through the trap where it traps the photons. And these atoms act as spies and give information about the photons without destroying them. This work had opened up a new era of experimental possibilities. They study both basic questions, like in quantum physics, like decoherence. And for the daily life, the realization of the most precise clocks ever seen is a reality with their work. And this Peirce Prize has also paved the first steps towards future quantum computers. that would say computers with speeds that would exceed everything and would be a dream for every programmer. Thank you.
Thank you, Professor Jonsson. Now I turn to Professor Per Delsting that will give us the first part of a more detailed presentation.
Thank you. So Professor Haroche and his collaborators have been able to capture light particles, that means photons, and they've used atoms to probe the state of the photons. So how do you capture light? Imagine yourself standing in an elevator with two mirrors. If you hold up your finger, you will actually see many fingers in the mirror. That's because the photons are bouncing back and forth between the mirrors before they reach your eyes many times. So this means that you can actually, if you have two mirrors like this, you can actually capture light between the mirrors. And you can send in atoms between the mirrors to control or to measure what the photons are doing. This is an idea that has been perfected by Serge Haroche's group like this. So they have done this for microwaves, and this, they can do this. They can actually capture just a single photon, and they can also do it for a sufficiently long time so that they have time to study the photons in this cavity. Next, please. So one of the things they've done is that they have been able to detect photons without destroying them. This is actually very hard to do. For instance, when I look at the people in this room right now, the photons that reaches my eyes are absorbed by my eyes and therefore destroyed. But it is actually possible to detect photons without destroying them. If you take atoms, specially prepared atoms, which are actually very unusually large, and they're also donut-shaped, and send it into this cavity, you can interact with the photons that are there, and that will change the state of the atom that comes out. So by measuring the atom when it comes out, you can tell whether there was a photon in the cavity or not when you measured. This is a little bit like eating the cake and having it too. This technology has been extended and refined by Serge Haroche's group, and they've done a number of very important experiments based on this technology. So in the quantum world, particles can take on two states at the same time. But in our ordinary world, big things cannot. So the quantum world is clearly very different from our ordinary world. And the process that explains how a system loses its quantum properties is called decoherence. And this is something that Serge Haroche has studied in detail. Some 80 years ago, Erwin Schrödinger proposed a thought experiment to show how strange the quantum world is. And it involved a cat that would be both dead and alive at the same time. This sounds very strange, but the point here is that this type of experiment can now be done in the laboratory, in fact, of both laureates. They can both produce states which are like these Schrödinger cat states. And they can follow this in detail quantitatively in time. So the big breakthrough was in 1996 when Serge Haroche's group managed to do this for the first time. Decoherence is very important because it allows us to understand our world, which is governed by quantum mechanics, but still it doesn't show these quantum properties on the large scale.
Thank you, Professor Delsing. And now Professor Anne Lullier will give us the second part of the more detailed presentation, please.
Sorry for that. So I'm going to describe the work of David Wineland and his group. So this is about ions. How do you capture an ions? Ions are atoms with an electric charge. So to capture an ion, you use electrodes, electric fields, as is represented here. How do you observe ions? You use photons, and more specifically laser light, to excite these atoms, and these atoms, these ions, decay by emitting light. So you look at the fluorescence that is emitted by these ions. And this is a photograph of actually not the ions themselves, but the light that is emitted by 3 beryllium ions that are captured in the same trap. David Weinand and his group have achieved extraordinary control over the states of an ion. An ion can have different internal states, which means that the electron can take different energy levels. They have been able to put an ion into one state, for example, down into the other state, up, or actually into a superposition of these two states, up and down. And an ion can also have different motion state, different vibration states. They can move one way, or they can move another way. This is indicated here as 0 or 1. Or they can actually, and this is the magic of quantum mechanics, move into 2 different ways at the same time. And Weinand and his group have shown that it is possible to actually transfer a superposition of internal state of an ion to a superposition of motion state of the ion. Why is it important? This is important in particular since it's the first very tiny steps towards what is called a quantum computer. Quantum computer is a dream that many physicists have, to build a computer that does not work with normal bits, 0, 1, as in a classical computer, but with quantum bits. This is the superposition of states. And it is predicted that quantum computers can be much faster for certain type of operation than classical computers. But it will take a little time before all of the laptops that you have here in this room will be replaced by quantum computer. Very important application of Weinand's work is optical clocks, the measuring of time. How do you measure time? You need something that oscillates, like the tip in a metronome, or this tip here in a very old clock. This is something that oscillates, tack, tack, tack. And the more the oscillation you have, the more precise your clock be. Today's clock is based on cesium atoms that work in the microwave range. With the work accomplished by Weinand and his workers, now we can use ion clock. An ion clock work in the visible, it's called optical range, with the possibility to have 10,000 more oscillations to measure time than with the cesium clock. And with this ion clock, they have achieved a precision which is as good as 10 to minus 17. What does it mean? That means that if such a clock had been existing since the beginning of our universe, like 14 billion years ago, then this clock would have gone wrong by at most 5 seconds. With that, I thank you for your attention.
Thank you, Professor Ullier. And just 30 minutes ago, we got hold actually of both laureates, and we will now see if we have one of them on the phone. I think it is Professor Aroche from Paris. Hello, Professor Aroche, are you there?
Yes, I am on the phone.
I think I told you that we are sitting here in the session hall at our academy in Stockholm, and I hope you are ready to answer some questions posed by the press here.
Yes, I am. I well, but I think I can answer questions.
Okay.
Hello, Professor. My name is Victoria Dyring. I'm from the Swedish television. We're live on air right now. First of all, congratulations.
Thank you very much.
How do you feel today?
It's hard to realize, you know. I was informed only 20 minutes ago, and I try not to think about that because I had a few phone calls to give in the meantime, but it's really fantastic.
How did you react when you got the message?
You know, in fact, I was lucky. I was in the streets and passing near a bench, so I was able to sit down immediately. I was walking with my wife going back home, and when I saw the area code 46, then I sat down. It was
You could see on the area code that this was coming up.
The Swedish code. Then I realized it was real, and it's really overwhelming.
Did you tell anyone yet?
Excuse me?
Have you told anyone yet?
Yes, in fact, immediately I called. First, I called my children, and then I called my closest colleagues, without whom I would never have gotten this prize, and they are very pleased. And one of them was lecturing, and I sent him a texto, and he answered, not thinking the phone, just called me back. I am in the middle of a lecture. We'll call back later. I texted back, interrupt your lecture and call me immediately. That's how I told him.
Could I ask you, how old are your children?
They are 42 and 40.
Okay, very glad now.
And in fact, I think my daughter does not know yet because we were not able to get it with her.
Sorry, come again, please.
Excuse me?
Could you please tell us once again?
I said that I think my daughter does not know yet because we are not able to get in touch with her and she's working, so I'm not sure she knows.
How will you celebrate?
I did not think about that. I think first thing I will do is to call my colleagues and my children, and we will have champagne at home. And in the afternoon, I will go back to the office and to the lab, and then really I don't. We will see. But the first thing I will do now is to try to have a private thing. But I think it will be very difficult because on the other phone line, it's calling all the time, and on the line that we are using here, I get a lot of beeps showing that people are trying to reach. I don't know what will happen.
Okay, Professor, we have some problems to hear you properly, some technical problems, but there's a big party coming up. Are you coming to Stockholm in December?
Of course.
I'm glad to hear that. Have a great day. Thank you.
Okay, thank you very much. Hello, is it over? Or?
Yeah, we have a second question there.
Hello, I'm Karin Boys from Swedish daily Dagens Nyheter. Big congratulations. I have two short questions. First, those quantum computers, when do you think they will exist in reality? And second question, those very extremely exact clocks, what can they be used for?
I heard only the first question. What was the second one?
First question, those quantum computers, when will they exist in reality? When can we use them? And next question, those clocks which are so exact, what can they be used for?
Okay. The first question, my answer is I really don't know. Fundamental research, and we are studying things, trying to understand the way atoms and photons behave at the particle level, and we learn a lot of things. To go into applications means that we're able to solve a lot of problems. I have always in the past skeptical about the application will be the one that the cases when big advances have been made in fundamental research, the application have not been the one was seeking in the first place. It has been the case of the laser, it has been the case of nuclear magnetic resonance, and I think the manipulation of quantum systems belong to the same kind of physics. There is a lot of things to learn at the fundamental level, and some application will come, but it's very hard to say which one. So maybe it will be some kind of computer, maybe some kind of useful quantum simulations, maybe in quantum communication, but Now, as for the second question, this is something which should be addressed more to my colleague Dave Wyman, who has been working in the clock, in the very precise clock business, and there are a lot of applications which can be thought of, like measuring. You know that these clocks are so sensitive that they can measure the gravitational shift with very high precision, and so the clock could be used to see some irregularities in the gravitational field for geological application, for earthquake predictions. This is one kind of application. Other kind of application are in the realm of fundamental physics, test of general relativity, for instance, and a lot of things, a lot of results could be expected from the experiments we carried in space stations using these very precise clocks.
We have a final question.
Yes.
Hi, Monsieur Arroche, and congratulations to the prize. My name is Louise. I work for the Associated Press. I was wondering, did you see this coming? Did you expect to win the Nobel Prize in Physics at all?
You know, it's a very difficult question. I did not see it coming as some high probability. You know, there are a lot of people in the world who deserve the prize, working in a lot of interesting areas, and I just consider myself as one of the possible choices, but I did not give that much probability. I did not think that it was highly probable, and I tried not to think about it in advance. So
Okay, I'm really sorry, I didn't hear you very well. Actually, can you repeat the last?
Yes, I just said that there are many people who deserve the prize, and the probability for each of us to get it is rather small. So I tried to not to expect too much, and I was not really expecting it, and especially I was not expecting it so much this year. So it's really a surprise, a wonderful surprise, and I am also very, very glad to share it with Dave Wyman, because he is a fantastic physicist, and you better judge other than yourself, and to be in his company is certainly a great pleasure for me and a great recognition.
Thank you.
Thank you very much. We've had some difficulties in hearing you. I'm looking at the physicist here, and I hope we promise a quantum telephone next time, so we'll have a high resolution. Thank you very much, Professor Arroche, and once again, warm congratulations, and we look forward to see you here in Stockholm in December for the Nobel Prize ceremony.
Thank you very much.
Thank you.
Thank you.
Bye.
Thank you.
So, do I have any questions from the press here to our experts? If not, I will close this press conference, and I wish you all welcome tomorrow, where we will announce the Nobel Prize in Chemistry. Thank you very much.